Hey there, everyone! Welcome back to our channel. Today, we're diving into a fascinating topic. What was the Big Bang? The Big Bang Theory is a cosmological model that explains the origin of the universe. It suggests that the universe began with a massive explosion, known as the Big Bang, about 13.8 billion years ago. This explosion created all the matter and energy in the universe, and it's still expanding today. The Big Bang Theory is supported by a wealth of scientific evidence, including the cosmic microwave background radiation, the existence of the cosmic microwave background radiation, and the discovery of the cosmic microwave background radiation. Introduction. What was the Big Bang? Have you ever wondered what came before the universe? What was the starting point for everything we see around us? The answer to this age-old question lies in one of the most extraordinary events in cosmic history, the Big Bang. But contrary to what the name suggests, the Big Bang wasn't an explosion in the traditional sense. It was the beginning of everything, the moment when time, space, and matter came into existence. In this video, we're going to dive deep into understanding what the Big Bang really was, how it all began, and why this event is so crucial for understanding the universe we live in. So, let's get started. The Big Bang is the event that marks the origin of our universe. It's the moment when the universe began to expand from an extremely hot, dense, and compact state, around 13.8 billion years ago. This expansion set in motion the formation of space, time, matter, and the very laws of physics that govern everything we see today. Before the Big Bang, there was no before in the traditional sense, because time itself began with the Big Bang. The universe was once confined to a point called a singularity, where the laws of physics as we know them break down. As the universe began to expand, it cooled down, allowing particles to form and eventually combine into atoms. This process eventually led to the formation of stars, galaxies, and all the structures that make up our cosmos. The evidence for the Big Bang comes from several key observations. One of the most significant is the cosmic microwave background radiation (CMB), a faint glow left over from the early stages of the universe. This radiation serves as a snapshot of the universe when it was just 380,000 years old, giving scientists crucial insights into the conditions of the early universe. The Big Bang Theory also explains the abundance of light elements like hydrogen and helium in the universe. According to the theory, these elements formed in the first few minutes of the universe's existence in a process known as Big Bang nucleosynthesis. Understanding the Big Bang isn't just about looking into the past, it also helps us understand the future of the universe. The ongoing expansion of space, which was set in motion by the Big Bang, continues today, and studying this can help us predict how the universe will evolve in the future. So, what was the Big Bang? It was the moment that everything we know began, a moment that still holds the keys to understanding the cosmos. By studying the Big Bang and the evidence it leaves behind, we continue to unravel the mysteries of our universe's origin and evolution. What is the Big Bang? The term Big Bang is often misunderstood. When we think of an explosion, we imagine a violent burst of energy, with debris flying outward from a specific point in space. However, the Big Bang wasn't an explosion in space, it was an expansion of space itself. Around 13.8 billion years ago, the universe was compressed into a single, incredibly dense point, often referred to as a singularity. This point contained all of the matter and energy that would eventually form everything we know: stars, planets, galaxies, and even time itself. The Big Bang was the moment when this singularity began to expand, and this expansion continues today. Rather than an explosion, it's more accurate to think of it as the rapid stretching of space, which led to the creation of the universe. The Big Bang refers to the moment when the universe began to expand from a singularity, an incredibly dense and hot point that contained all of the matter and energy of the cosmos. It wasn't an explosion in space. Rather, it was the rapid expansion of space itself. This event occurred about 13.8 billion years ago and marks the origin of the universe as we know it. In the first moments after the Big Bang, the universe was extremely small, dense, and hot, with temperatures soaring trillions of degrees. As it began to expand, the universe cooled, allowing particles to form. These particles eventually combined into atoms, stars, galaxies, and all the structures we observe today. It's crucial to understand that space itself was stretching during the Big Bang, and it's still expanding today. This expansion doesn't mean that matter is spreading outward into a pre-existing space. Instead, space itself is growing, causing galaxies to move away from each other. This phenomenon is still happening now, as evidenced by the redshift of light from distant galaxies and the discovery of the cosmic microwave background radiation. So, the Big Bang wasn't an explosion in space, but rather the beginning of space itself. It's the starting point for everything: time, space, matter, and energy. The universe has been expanding ever since, and understanding this process helps us unlock the mysteries of its past and future. The early stages of the universe. What happened immediately after the Big Bang? In the first few seconds after the Big Bang, the universe was extremely hot and dense. In fact, it was so hot that atoms could not yet form. The only things present were elementary particles, quarks, electrons, and photons zooming around in a violent and chaotic environment. It was a place where conditions were beyond anything we can imagine today. As the universe expanded, it began to cool. This cooling allowed for particles to combine and form protons and neutrons. These particles later combined to form the first simple atoms, primarily hydrogen and helium, the building blocks of stars. In the first moments after the Big Bang, the universe was an incredibly hot and dense place. Temperatures reached trillions of degrees, so hot that atoms couldn't form. Instead, the universe was filled with elementary particles, such as quarks, electrons, and photons, all moving rapidly and interacting in a highly energetic environment. During the very early stages, just a fraction of a second after the Big Bang, particles called quarks combined to form protons and neutrons, the building blocks of atoms. This stage was incredibly chaotic, as the universe was still too hot and energetic for matter to remain stable. As the universe continued to expand, it began to cool down. With the cooling, protons and neutrons started to combine, forming atomic nuclei in a process called nucleosynthesis. During this phase, hydrogen and helium nuclei were created, along with tiny traces of other light elements like lithium. This period, which lasted for just a few minutes, was crucial because it set the stage for the formation of the first atoms. However, the universe remained opaque for hundreds of thousands of years because it was still too hot for electrons to combine with atomic nuclei to form neutral atoms. The universe was a soup of charged particles and light, which couldn't travel freely through space. It wasn't until about 380,000 years after the Big Bang that the universe had cooled enough for electrons to finally combine with nuclei, forming the first atoms. This marked the recombination era, and it allowed light to travel freely, giving birth to the cosmic microwave background (CMB) radiation, faint radiation that we can still detect today. This light serves as a snapshot of the universe at this early stage, offering us a glimpse into the conditions that existed just after the Big Bang. In summary, the early stages of the universe were marked by rapid expansion, extreme heat, and chaotic conditions. But as it cooled, simple particles formed into protons, neutrons, and eventually the first atoms, setting the stage for the formation of stars, galaxies, and everything that came later. Cosmic inflation, the universe's rapid growth. One of the most important concepts in understanding the Big Bang is the idea of cosmic inflation. This theory suggests that in the first fraction of a second after the Big Bang, the universe expanded incredibly rapidly, far faster than the speed of light. In a fraction of a second, the universe expanded by a factor of at least 10^26 in size. This rapid expansion smoothed out the universe, making it more uniform, and helps set the stage for the formation of galaxies, stars, and the structures we see today. It also explains why the universe appears so homogeneous on large scales. Without inflation, the universe would be much more irregular. Cosmic inflation is one of the most fascinating and important concepts in understanding the Big Bang and the early universe. The theory of inflation proposes that, in the first tiny fraction of a second, roughly 1036 to 1032 seconds after the Big Bang, the universe expanded at an extraordinary rate, far faster than the speed of light. During this brief period of rapid expansion, the universe grew by an immense factor, at least 1026 times its size, causing the universe to stretch out in a manner that is hard to imagine. This expansion is referred to as cosmic inflation, and it is crucial for explaining many of the features we observe in the universe today. Why is cosmic inflation important? Smoothed out the universe. The rapid inflationary period flattened out irregularities and smoothened the universe on large scales. This helped create a more uniform and homogeneous universe, eliminating any major unevenness in its early structure. Without this smoothing effect, we would see a much more chaotic universe today, with areas of dense matter and vast voids that don't follow the patterns we observe now. Explains the large-scale uniformity. One of the key challenges in understanding the universe was why distant parts of the universe separated by vast distances seem to be so similar in temperature and structure. Inflation solves this mystery. The rapid expansion allowed regions that were once in close contact to spread out evenly across the universe, explaining the uniformity of the cosmic microwave background (CMB) radiation. Set the stage for structure formation. The slight variations or quantum fluctuations in the density of matter that survived inflation played a critical role in the later formation of galaxies and clusters of galaxies. These fluctuations acted as seeds for the structures that formed as the universe continued to expand and cool. How does inflation work? During inflation, the universe was dominated by a form of energy that drove its rapid expansion. This energy came from a hypothetical field called the inflaton field, which caused the universe to expand exponentially. After inflation ended, the energy from the field transitioned into the matter and radiation that we see today, kick-starting the formation of particles and eventually the structures of the universe. The legacy of inflation. Cosmic inflation not only explains the large-scale structure of the universe, but also provides a mechanism for how the universe could have started from a very hot, dense, and chaotic state and evolved into the vast cosmos we observe today. While inflation was a brief moment in the universe's history, its effects are still seen in the uniformity of the universe and in the patterns we see in the cosmic background radiation. In essence, cosmic inflation was a rapid growth spurt that took place in the universe's very early moments, shaping the universe into the vast and structured cosmos we now explore. Formation of matter and elements. As the universe cooled down, particles began to form atoms. In the first few minutes after the Big Bang, nuclear reactions led to the creation of the first light elements, primarily hydrogen, helium, and traces of lithium. These elements were crucial for the formation of the first stars and galaxies. For the first several 100,000 years, the universe was a hot, dense plasma of free electrons and atomic nuclei. But eventually, as it cooled further, electrons combined with nuclei to form neutral atoms. This process, known as recombination, allowed light to travel freely for the first time, and the universe became transparent. This moment is marked by the cosmic microwave background (CMB), a faint glow that we can still detect today, offering us a glimpse of the universe in its infancy. Formation of matter and elements. After the Big Bang, the universe began to cool rapidly. In the first few minutes, as the temperature decreased, nuclear reactions took place, leading to the formation of the universe's first light elements. These reactions, known as Big Bang nucleosynthesis, created primarily hydrogen, the simplest element, helium, and small amounts of lithium. These elements are the building blocks of the matter that would later form stars, galaxies, and everything else in the universe. The plasma era. For the first several 100,000 years, the universe was an extremely hot, dense plasma of free electrons and atomic nuclei such as protons and helium nuclei. At these temperatures, the universe was so hot that electrons couldn't stay bound to atoms. They would immediately be separated by the intense energy. As a result, the universe was opaque to light, as photons, light particles, constantly scattered off the free electrons. recombination, and the birth of light. As the universe continued to expand and cool, it eventually reached a point where the temperature dropped enough for electrons to combine with atomic nuclei. This process, called recombination, allowed the formation of neutral atoms, primarily hydrogen and helium. This marked a significant turning point in the universe's history because, for the first time, light could travel freely through space. With the formation of neutral atoms, the photons that had previously been scattered were no longer impeded, and the universe became transparent. This moment is crucial in cosmology because it marks the release of the cosmic microwave background (CMB) radiation, which is the afterglow of the Big Bang. The CMB is a faint, uniform radiation that fills the universe and serves as a snapshot of the universe when it was just 380,000 years old. We can still detect this radiation today, and it provides valuable information about the state of the early universe. Legacy of early elements. First elements, hydrogen and helium, formed the foundation for everything that came later. These elements began to clump together under gravity, eventually leading to the formation of the first stars and galaxies. These stars then began the process of nuclear fusion, creating heavier elements in their cores, which would later be spread throughout the universe through supernova explosions. These heavier elements would become the building blocks of planets, life, and everything we observe in the universe today. In summary, the cooling of the universe allowed for the formation of the first atoms and elements, and the process of recombination allowed light to travel freely for the first time. The CMB radiation, still detectable today, provides a glimpse into this early, opaque universe. These events set the stage for the formation of stars and galaxies, marking the beginning of the universe's complex evolution. What is the CMB? The CMB is a uniform radiation that fills the entire universe, and it's a remnant from a time when the universe had cooled enough for neutral atoms to form. Before this time, the universe was a hot, dense plasma where electrons and nuclei couldn't combine to form atoms, and light was constantly scattered by free electrons. As the universe cooled and atoms formed, photons-like particles were able to travel freely for the first time, and the CMB was released. This moment, known as recombination, marks when the universe became transparent to light. The CMB is a faint, microwave radiation that we detect everywhere in the universe. It is remarkably uniform, with a temperature of about 2.7 K, just above absolute zero. However, within this uniformity are tiny variations in temperature, on the order of just a few millionths of a degree, that provide us with valuable information about the universe's early conditions. Tiny fluctuations, seeds of structure. Although the CMB appears uniform to the naked eye, it contains tiny fluctuations, differences in temperature that have been carefully mapped by advanced telescopes like the Planck satellite. These fluctuations are not random. They are believed to be the seeds from which galaxies, stars, and larger cosmic structures would eventually form. These small variations in density caused by quantum fluctuations in the early universe acted as the starting points for gravitational collapse, leading to the formation of the complex structures we observe in the universe today. Importance of the studying the CMB gives scientists a direct window into the conditions of the universe when it was still in its infancy. It offers insights into the composition and evolution of the early universe, helping cosmologists test and refine their models of how the universe began and evolved. For example, the CMB provides evidence for the cosmic inflation theory, which suggests that the universe expanded exponentially during the first moments after the Big Bang. Additionally, the CMB has allowed scientists to determine key properties of the universe, such as its age, density, and rate of expansion. By comparing the measurements of the CMB with theoretical models, cosmologists have been able to refine our understanding of the universe's structure and history. Conclusion: the cosmic microwave background is one of the strongest pieces of evidence for the Big Bang, providing a snapshot of the universe when it was just 380,000 years old. It is the afterglow of the Big Bang, a faint radiation that carries crucial information about the early universe. The tiny temperature fluctuations in the CMB are the remnants of the small differences in density that led to the formation of galaxies and cosmic structures. By studying this ancient radiation, we continue to learn more about the origins and evolution of the universe. Formation of galaxies and stars. The birth of the universe. As the universe continued to expand and cool, gravity began to play a crucial role. It caused hydrogen and helium atoms to come together, forming the first stars and galaxies. These early stars were not like the ones we see today. Many of them were much larger and burned much hotter and faster. Over time, these stars began to die, and in their deaths, they created heavier elements like carbon, oxygen, and iron. These elements were later scattered across the universe, and through the process of star formation, they became the building blocks of planets, moons, and life itself. Formation of galaxies and stars. The birth of the universe. As the universe continued to expand and cool after the Big Bang, gravity began to have a significant impact on the distribution of matter. The force of gravity pulled together the first hydrogen and helium atoms, which were the dominant elements in the early universe. This process led to the formation of the first stars and galaxy structures that would form the foundation of the universe as we know it. The first stars, hot, massive, and short-lived. The first stars formed several hundred million years after the Big Bang, in a period known as the Cosmic Dawn. These early stars, often referred to as population 3 stars, were very different from the stars we observe today. They were much larger, hotter, and more massive than modern stars, and they burned through their fuel much faster. Due to their size and high temperatures, these stars could generate the extreme conditions necessary for the creation of heavier elements in their cores. Stellar evolution and supernova explosions. The early stars were not meant to live long lives. Their immense size and the speed at which they consumed their nuclear fuel meant that they burned out quickly, often in just a few million years. When these massive stars reached the end of their lives, they underwent supernova explosions, violent events that marked the death of a star and released vast amounts of energy and matter into space. These supernovae were crucial for the creation of heavier elements. During these explosive events, elements like carbon, oxygen, and iron were synthesized and scattered throughout space. These elements would go on to play a critical role in the formation of future stars, planets, and even life itself. Formation of new stars and planets. After the supernova explosions, the heavier elements mixed with the remaining hydrogen and helium gas, providing the raw material for the formation of new stars. As gravity continued to pull matter together, new stars began to form from the clouds of gas and dust left behind by the deaths of previous stars. Over time, these new stars formed in galaxies, vast collections of stars, gas, and dark matter bound together by gravity. In some regions of these galaxies, the gas and dust coalesced to form planetary systems. The presence of heavier elements allowed for the formation of rocky planets, moons, and eventually the conditions that could support life. In this way, the death of the first stars played a critical role in enriching the universe with the elements necessary for the formation of planets like Earth. The ongoing cyclic process of star formation, stellar death, and the creation of heavier elements has continued throughout cosmic history, leading to the diverse range of stars, galaxies, and planets we observe today. As new stars form from the remnants of old ones, the universe gradually becomes richer in elements, with each generation of stars contributing to the complexity and diversity of the universe. Conclusion: the formation of galaxies and stars marked a crucial chapter in the birth of the universe. Gravity helped gather the first hydrogen and helium atoms, leading to the creation of the first stars. These early stars, though short-lived, created the elements necessary for future star systems, planets, and life. The cycle of star birth and death has continued throughout the history of the universe, shaping the cosmos and ultimately leading to the rich, diverse universe we see today. Ongoing expansion. The universe is still growing. The Big Bang didn't stop the universe from expanding. In fact, it's still expanding today. This expansion was first discovered in the 1920s by astronomer Edwin Hubble, who observed that distant galaxies were moving away from us. The farther a galaxy was, the faster it was receding. This observation led to the understanding that the universe is still stretching out from its initial starting point. The discovery that the expansion is actually accelerating due to mysterious dark energy has become one of the most intriguing areas of research in cosmology. Ongoing expansion. The universe is still growing. The Big Bang may have been the origin of the universe, but it didn't mark the end of expansion. In fact, the universe is still expanding today, and this expansion is a key feature of the cosmos. The ongoing stretching of space is one of the most significant aspects of our universe's evolution, and it was first observed in the 1920s by astronomer Edwin Hubble. Edwin Hubble's groundbreaking observations revealed that distant galaxies were moving away from us, and the farther a galaxy was, the faster it appeared to be receding. This discovery led to what we now call Hubble's law, which showed that the universe was expanding, and it was expanding everywhere. The galaxies were not just moving through space, but rather, space itself was stretching, causing the galaxies to move apart. This observation fundamentally changed our understanding of the universe. Instead of being static, the universe was dynamic, stretching and evolving over time. Hubble's findings also suggested that, if we could trace the movement of galaxies backward, we would reach a point where all matter was concentrated in a singularity, the point from which the Big Bang occurred. The expanding universe. Today, since Hubble's discovery, we have learned that the expansion of the universe is not only continuing but accelerating. In the late 1990s, astronomers observed distant supernova and realized that galaxies were moving away from each other at an increasingly faster rate. This led to the understanding that the universe's expansion is accelerating, a surprising and puzzling discovery. Dark energy. The mystery behind the acceleration cause of this accelerated expansion is still one of the greatest mysteries in cosmology. Scientists have proposed the existence of a mysterious force called dark energy, which is thought to make up about 68% of the universe. Dark energy seems to counteract gravity and drive the expansion of the universe faster over time. However, its exact nature remains unknown, and it is one of the most intriguing areas of research in modern cosmology. What does ongoing expansion mean for the future? As the universe continues to expand, galaxies are moving farther apart, and the space between them is growing. If the current rate of acceleration continues, distant galaxies will eventually move beyond our observational reach. This expansion has profound implications for the ultimate fate of the universe. Theories range from a continued expansion leading to a cold, dark universe where stars burn out and galaxies drift apart, to potential models like the Big Freeze or Big Rip, where the forces driving expansion could eventually tear apart galaxies, stars, and even atoms. Conclusion: the universe is not a static place. It has been expanding since the Big Bang and continues to grow today. Hubble's discovery that galaxies are moving away from us provided the first evidence of this expansion, and the realization that this expansion is accelerating due to dark energy has opened up new questions about the universe's ultimate fate. As scientists continue to study these phenomena, the ongoing expansion remains one of the most fascinating aspects of the cosmos, reshaping our understanding of space, time, and the universe itself. Unanswered questions. What happened before the Big Bang? While the Big Bang theory provides a solid explanation for the origins of the universe, there are still many unanswered questions. For example, what happened before the Big Bang? Could the universe have existed in some form prior to this event? Some scientists suggest that the universe could be part of a multiverse, a collection of infinite universes that exist independently of one another. Others propose the idea of cyclic models, where the universe undergoes repeated cycles of birth, death, and rebirth. These questions remain some of the biggest mysteries in modern physics, and researchers continue to search for answers. Unanswered questions. What happened before the Big Bang? While the Big Bang theory has provided a comprehensive explanation for the origin and early evolution of the universe, it leaves many important questions unanswered. One of the most profound and perplexing questions is what happened before the Big Bang? Did the universe exist in some form prior to this event, or was the Big Bang the absolute beginning of everything, including time and space? Could the universe have existed before the Big Bang? The concept of time itself is deeply tied to the Big Bang. According to most models, time, space, and all the matter and energy in the universe came into existence at the moment of the Big Bang. This raises the question, if time itself began with the Big Bang, what does it mean to talk about before the Big Bang? Some scientists suggest that our current understanding of time and space may not fully apply to the conditions that existed before the Big Bang. According to these ideas, it's possible that the universe, whether in a different form or through different physical laws, existed before the Big Bang. However, this remains speculative, as our current theories cannot provide a concrete answer. The multiverse theory. Only intriguing hypothesis is the idea of a multiverse, a collection of potentially infinite universes that exist independently of one another. In this scenario, our universe could be just one of many, each with its own set of physical laws, constants, and histories. The multiverse theory suggests that the Big Bang may not have been a unique event, but rather one of many occurrences in an infinite cycle of universe creation. There are different versions of the multiverse theory. Some propose that universes form from quantum fluctuations, while others suggest that our universe may be part of a larger bubble of universes, each in its own phase of expansion. However, the multiverse hypothesis, while fascinating, is still highly speculative, and there is currently no experimental or observational evidence to support the existence of multiple universes. Cyclic models of the universe. Another idea that some scientists propose is the concept of cyclic models of the universe. These models suggest that the universe does not have a single beginning point, but instead undergoes repeated cycles of birth, death, and rebirth. In this view, the Big Bang could represent the beginning of a new cycle, with each previous cycle having its own Big Bang and eventual collapse. One version of this idea is the ekpyrotic model, which proposes that the universe is the result of a collision between two higher-dimensional objects called branes. In this scenario, our universe might have been created by the collision of these branes in a higher-dimensional space. After the Big Bang, the universe would expand, eventually slow down and collapse, only to give birth to a new cycle. These cyclic models offer an interesting alternative to the one-time Big Bang scenario, but also come with their own challenges and unanswered questions. How exactly do these cycles work, and how can we test them? The limits of current physics. Search for answers to these questions lies at the frontier of modern physics. Current theories of quantum mechanics and general relativity are powerful tools for understanding the universe on both very small and very large scales, but they do not fully align in extreme conditions like those that would have existed before or during the Big Bang. To answer questions about the origin of the universe and what happened before it, physicists are seeking to develop a theory of quantum gravity, which would unify these two pillars of physics. Conclusion. Despite the tremendous progress made by the Big Bang theory in explaining the origins and evolution of the universe, many questions remain unanswered. What happened before the Big Bang? Could the universe be part of a larger multiverse, or is the universe cyclic, going through repeated cycles of birth and rebirth? These questions are some of the most profound mysteries in modern physics, and researchers are working hard to explore them. As our understanding of the universe deepens, new theories and ideas may eventually help us uncover answers to these fundamental questions. Conclusion. Understanding the Big Bang and our universe's Big Bang wasn't just an explosion, it was the beginning of everything. It marked the start of time, space, and all the matter that makes up our universe. Understanding the Big Bang not only helps us learn about how our universe began, but also provides us with a deeper understanding of the fundamental forces that shape everything around us. As scientists continue to explore the far reaches of space and time, we might one day uncover even more about the origins of the universe, and perhaps even answer some of the most profound questions humanity has ever asked. What happened before the Big Bang? Are we alone in the universe? And, perhaps most intriguingly, what is the ultimate fate of our cosmos? Conclusion. Understanding the Big Bang and our universe's Big Bang wasn't just an explosion. It was the beginning of everything, the birth of time, space, and all the matter that forms our universe. By studying the Big Bang, scientists have unlocked a deeper understanding of not only how the universe came to be, but also the fundamental forces that govern everything around us, from the smallest particles to the vast galaxies. Through the Big Bang, we have learned how space expanded, how matter formed, and how the universe continues to evolve. Concepts like cosmic inflation, the formation of elements, and the cosmic microwave background have given us glimpses into the universe's infancy, revealing how stars, galaxies, and even the elements essential for life came into existence. However, the Big Bang Theory doesn't provide answers to all our questions. As our exploration of the universe continues, we are faced with even bigger mysteries. What happened before the Big Bang? Could the universe be part of a multiverse? How did dark energy come into play? And what is the ultimate fate of the cosmos? These questions push the boundaries of human knowledge and fuel our quest for deeper understanding. As scientists continue to push the limits of technology and theory, we might one day uncover answers to these profound questions. The mysteries of the universe are far from over, and each discovery brings us closer to understanding the origins and future of everything we see and experience. The journey to understanding the Big Bang and our universe is ongoing, and it promises to continue to reveal the most fundamental truths about existence itself. So, there you have it. The Big Bang Theory is a compelling explanation for the origin of the universe. If you enjoyed this video, please give it a thumbs up, and don't forget to subscribe for more fascinating topics. Thanks for watching, and see you next time.